All right, so we're on page 29 of chapter 9. We're in section 9.8. So this next section is going to talk about some non-parametric alternatives. We're going to first talk about what is the Wilcoxon-Signed rank test, and that's for the one sample test, and then we're going to talk about the two sample test, which is the Mann-Whitney U test. All right, so suppose that your data turns out to be pretty substantially non-normal, but you still want to run something like a t-test. This situation occurs a lot in real life, so like for our AFL winning margins data, for example, the histogram, the QQ plot, and the Shapiro-Wilk test, it all made it very clear that the normality assumption was violated. So this is the situation where we can use the Wilcoxon test. So like the t-test, the Wilcoxon-Signed rank test, it comes in two forms. So there's the one sample and the two sample Wilcoxon tests, and they're used in more or less the exact same situations as the corresponding t-tests. But unlike the t-test, the Wilcoxon test does not assume normality, which is good. In fact, they don't make any assumptions about what kind of distribution is involved. So, in statistical jargon, this makes them non-parametric tests. So while avoiding the normality assumption is nice, there is a drawback. So the Wilcoxon test, it's usually less powerful than the t-test. There is typically a higher type 2 error rate. We're not going to discuss the Wilcoxon tests in great detail, just like we went through the t-tests in really great detail, but we will give a really brief overview of both the one sample test and give an example of the Wilcoxon-Signed rank test, and we're going to also give the two sample test example, and for that we're going to use the Mann-Whitney U test. So here we go, we're on page 29, we're in section 9.8.1. So the Wilcoxon-Signed rank test is also known as the one sample Wilcoxon test. It is a non-parametric alternative to the one sample mean t-test or a paired means t-test. So as an example, suppose that we're interested in finding out whether taking a statistics class has any effect on the happiness of students. So the data that we're going to use for this example is the data in the happiness.csv file. So what is measured in this file is the happiness of each student before they took the stats class and after taking the stats class. The change score is the difference between the two scores. So just like we saw with the t-test, there's no fundamental difference between doing a paired sample t-test using before and after versus doing the one samples test using the change scores. So as before, the simple way to think about the test is to construct the tabulation frequency table. So the way that we can do this is to take those change scores that are positive differences and tabulate them against all of the complete sample. So again, we're on page 29 and we can see what this frequency table looks like. You'll end up with this table, and so on the left side we see positive differences, and on the top we see all differences. So if we count up all of the tick marks in this chart, we get a test statistic of W equals 7. Big W equals 7. And as before, if our test is two-sided, then we can reject the null hypothesis when W is very large or very small. So We're not going to panic and try to do this by hand. We're going to have JASP do those calculations for us. We're going to move on to page 30. So we're going to open up our JASP. And we're going to do our example on page 30. So we're going to maximize this, okay? And then we're going to open up the happiness data set. So we're going to go into our downloads, and we're going to choose the happiness data set, open, and first we could treat this as a single sample test using the change variable, which was computed in the after minus before section. And so as we can see, we have the ID of the participant, we have the before and after values, as well as the change value column. So let's go ahead and open up the t-test here and do this example. We're going to do the one sample t-test, so select one sample t-test. And then we're going to move the change variable into the variables box. And then we're going to see the output over here. All right, so we have a t-score for the one sample t-test with the degrees of freedom and the p-value, okay? And then we're going to go under tests here, all right? And we can see the default is the student test, but we're going to uncheck the student test and we're going to check the Wilcoxon-Signed rank test this time. But if we want to compare those just for fun, we could keep them both checked. So now we're going to scroll down page 30 and we're going to check our output against the figure 9.23 output, and we're going to look at our W test statistic and p-value. So let's take a look. Yes, we get the Wilcoxon big W statistic as 7.000, and then we get the we can actually get our Z test as well. Hold on, we're going to follow the book example so we don't confuse anyone. So we did our one sample t-test first, and we get our change value of 7.000 and our p-value of 0.037. And this is for our Wilcoxon test, which is what we have checked off. And that is for the change value. Then we're going to also run this as a paired sample means test. And so we're going to run one more plot under t-test, and we're going to choose the paired sample t-test, okay? And this is where we do the after and before, okay, in that order. So I'm sorry, we're going to do after, move that, and before, and we're going to move that, which we were playing around with this type of data earlier. So we move those over to the variables box, and then we go under test, and we uncheck the box which defaults to student, and we check the Wilcoxon-Signed rank test. All right, and we can now see the data is matching the data presented in figure 9.23. So we have our paired samples t-test and our Wilcoxon rank test is 7.000, and then the z-score is negative 2.090, and the p-value is 0.037. So we have done two types of output. We ran the one sample test and the paired sample test first. And we're going to now move into the very, very last concept, which is the Mann-Whitney U-test. So we're all done with learning about the Wilcoxon-Signed rank test. Now we're still on page 30, and we're moving into section 9.82. So what is this Mann-Whitney U-test? So what if we want to compare the two independent groups, but assumptions aren't meant to run an independent means t-test? And that is where we can now use this Mann-Whitney U-test. So the Mann-Whitney U-test, it does not compare means, rather it compares distributions by looking at all of the rankings. So as an example, suppose we're looking at the scores of 10 people on a test. And since our imagination can fail us completely, let's say that this is a silly test of awesomeness, all right? And there are two sample groups of people, group A and group B. So we might be curious to know if the two groups differ in terms of their self-reported or self-assessed awesomeness. So the data are going to be in our awesome CSV file. So let's go grab that. So we're going to maximize this. We're going to go to our hamburger. We're going to open our downloads, and we're going to look for awesome. Here it is. Open. So, again, we have 10 values reported, right? We have the identifications of participant 1 through 10. We have our scores, and we have the grouping of A or B, all right? So this data, again, is in the awesome.csv file. There are two variables apart from the usual identification variable. There's scores and group. Now we're going to go to page 31. So as long as there are no ties, for example, people with the exact same awesomeness score, so we can look through. I don't see anyone with the same self-reported score. Then the test that we want to do is pretty simple. All we have to do is construct a table that compares every observation in group A against every observation in group B. And whenever the group A data is larger, then we can place a check mark in the table. So as we can see on page 31, this is already done for us. We have group A on the left, group B across the top, and we have our check mark. So When we count up the number of check marks, this is our test statistic, or W raised to the 16. Again, the actual sampling distribution for the big W is somewhat complicated, so we're not going to go through those details. For the purposes of this introduction, it's sufficient to note that the interpretation of big W is qualitatively the same as the interpretation of the T or the Z test statistics. So that is, if we want a two-sided test, then we would reject the null hypothesis when the big W is very large or very small. But if we have a directional or one-sided hypothesis, then we're only going to use one or the other. So, as you can imagine, as the sample size increases doing our Mann-Whitney U-test by hand, it would become pretty difficult. So for that reason, we're going to plug this all into our JASP software. So again, we have already opened this awesome CSV file, which is silly, but we're going to go through this example. And then we're going to compare the scores across the two levels of the groups, group A and B. So how do we do it? So we're going to go into our t-test, okay? We're going to open up the independent samples t-test. We're going to move our scores to the dependent variables box, and then we're going to split it by the grouping variable. So we move the grouping to the grouping variables box. So then under our tests, okay, we are going to uncheck the student t-test, and we're going to check the Mann-Whitney. And the results of our output will be shown in table 9.24. So let's take a look. 9.24, and we get a U value, so the Mann-Whitney U test is 3.00, p-value is 0.056, so that looks like everything came out properly. So if we were going to practice summarizing the data, again, we could grab the descriptive statistic here to help us. So we could say that in a Mann-Whitney test was used to compare the awesomeness, a silly scenario, but the awesomeness of participants in group A, where the N equaled 5 and the mean difference, okay, was 10, and then for group B, N equals 5, and the mean was 12.5, mean difference. And so the results of that test came out to be not statistically significant, because as we can see, our p-value was greater than 0.05. It was 0.056. And again, we can report U equal 3 and our p-value of 0.056. So note that instead of reporting the mean and the standard deviation, we just reported the medians in this example. In place of these medians, we could also report the mean ranks, which again are obtained in our software when you run this test by checking the descriptives box, which we did, okay? And to summarize, non-parametric tests like the Wilcoxon-Signed rank test and the Mann-Whitney U test, okay, let's go back here. So the Mann-Whitney U-test and the Wilcoxon signed rank tests, right? These are the non-parametric tests. So in summary, non-parametric tests like the Wilcoxon and the U-test, they provide valuable alternatives when the assumptions of parametric tests like normality of the sampling distribution are violated. However, it is important to note that these tests, they are, again, less powerful than the parametric tests. So we're only going to recommend using them in cases where the assumptions of the t-test are violated or they're not met. All right, so then we're going to summarize we're going to go back and summarize, right? So why are t-tests used in statistics? That was the whole point of going through this chapter. So we did cover a lot of content, and so what we went over was the one sample mean z-test, okay? The one sample mean t-test, we went over the two independent samples t-test, the student t-test, okay, as well as the Welch test. We went over the paired means t-test, and then we went through the non-parametric alternatives, which included our Wilcoxon-Signed rank test and the Mann-Whitney U-test. There is also a really nice flow chart that appears on page 33, and we're going to go through that before we conclude this chapter. And that is going to be located on page 33 in figure 9.25, where we can find our flow chart that we're going to use to summarize when to use each of these tests. And we also did in this chapter, in addition to the hypothesis tests, we explored Cohen's d and effect size, and we went through the three different methods for checking normality. So it does, for newbies, it will feel like a lot of new content, but once we go through the similarities between the procedures, it will make a lot more sense. The Z and the t-test statistics, they do all follow the same structure of difference in means divided by standard error. And then also the Cohen's d, it is similar, except the denominator happens to be the standard deviation. So remember, when doing the introductory lessons and in real life, we're going to be using for just the general learning of how to use the software, we're going to use the JASP software to conduct our tests. And next we're going to skip to page 33, and we're going to go through the flow chart. So let's remember that sometimes we have, hold on, I lost my page. So sometimes we might have the one sample, right? We may have a one sample mean test, like a z-test or a t-test, okay? So when we have the one sample mean, first we want to ask ourselves, how many measurements do we have? So if we have one measurement, then we would ask ourselves, is the sampling distribution normal? So if it is, then we would ask ourselves, okay, then is the standard deviation known? And if the standard deviation is known, we would do the one sample mean z-test. Then if we back up and we say, okay, we have a one sample, and then we ask, how many measurements do we have? So if we again have one measurement, we'll ask, is the sampling distribution normal? But if it is not normal, okay, then we're going to just go ahead and do the Wilcoxon-Signed rank test. So it's actually quite simple. So if our sampling distribution is normal and we know the standard deviation, we can do the one sample mean z-test, right? If we know the standard deviation, but if we don't, we will do the one sample mean t-test. Then if we back up and we say, okay, we have one sample and we ask, is the sampling distribution normal? And the answer is no. Okay, that means that we're also not going to know the standard deviation, right? So not only do we not have the normal distribution, we don't know the standard deviation, so we're just going to default right away, and we're going to jump to the Wilcoxon big W signed rank test. All right. Now, if we have one sample and we ask ourselves, how many measurements do we have? And now we have like two measurements. For example, we have a paired data set. Then we're going to ask ourselves, okay, so now is the sampling distribution normal, right? We're going through the assumptions. If we say, yes, actually, the sampling distribution is normal, we can then do the paired samples t-test, but if we have the two measurements, okay, and we ask ourselves, is the sampling distribution normal, but the answer is no, what do? We default to the Wilcoxon test again, big W. All right, then there's one more really simple scenario where we go to the two independent samples t-test. So again, we go back and we ask ourselves about the assumptions. So is our sampling distribution normal? If it is, we can go ahead and we can do the students' two independent samples t-test, right? The two independent means t-test. But if we say, all right, well, I have two independent samples, and we ask ourselves, is the sampling distribution normal? And the answer is no. This is where, when we have the two independent samples, that we go to the U-test, the Mann-Whitney U-test. All right, so really, we have scenarios where we focused on the one sample mean z-test, the one sample mean t-test, the Wilcoxon-Signed rank test, the big W, the paired samples t-test, and then we go back to the two samples means t-test versus the U-test or the Mann-Whitney U-test, okay? So again, I will encourage everyone to go to page 33 and review the diagram, which is figure 9.25.